Hey everyone, welcome to another Facebook Live from Flyin Miata. My name is Jeremy and I am a doer of things here at Flyin Miata. And today what we want to talk about is timing. And so how I want to start this is I want to start off with some just kind of basic, real high level overview stuff about timing. And then we actually got a lot of questions from you guys. So we'll be able to dig into some of these questions and see where some of those things lead. So let's get started. So what is timing? In an engine, here we have a BP 4W. You've got some basic things that you need to make it run, right? It should be pretty obvious. You've got your air that comes in, which is always better when it's pressurized by an FM turbo. You've got spark, and you've got fuel, which got your injectors. And so the computer's job is to meter the air that's coming in, and it knows for however much air is coming in to deliver a certain amount of fuel vapor to mix with that air. And then it also has to fire the spark at the right time so that the combustion is efficient and effective. And that's your timing table. So there's a three-dimensional timing table that's going to be in the computer, whether it's a stock computer or an aftermarket computer. And that defines when the spark fires for any given point on the table, which has the axes of load and RPM, right? So pretty simple. The theory is the simple part. How to set it up is really where the challenge comes in. So how does the computer know what the timing is? Well, there's a couple sensors. On an NA, you've got your cam angle sensor on the back of the head here, whether it's a 1.6 or a 1.8. On an NB, you've got a crank sensor here, and then you've also got a cam sensor. And then in a VVT, the exact same thing will be back here. So you say, okay, well, why do you have two? Well, to be efficient for fueling, these things run in sequential fueling, but they actually run in batch ignition. And what's that mean? So for sequential fueling, it has to know when your cylinder cycle is so that it can fire, well, here, I'm just trying to back into this real high level. So pretend you've got 4 pistons. By the way, here's a Flyin Miata piston. You can see that we've got our ceramic coating on the crown and our Xylan coating on the skirt. And this is custom pistons that Wiseco makes specifically for us to our specs. And so you've got 4 of these. And in this engine, these 2 go up and down the same, and then the 2 in the middle go up and down the same, but 180 degrees off. And so it's got to know when is the number 1 event versus when's the number 4 event. So if you have a standalone with timing, you could just run with this sensor, but you can only run in batch. And what that means is both of these are going to fire at the same time, and both of these are going to fire at the same time. As soon as you introduce a cam sensor, the cam sensor is able to delineate where's the number 1 versus the number 4. So even though that these 2 are both moving at the same time, it's going to know, okay, now I fire on number 1, now I fire on number 4, etc. So that way you can have sequential fueling, and with a standalone, for example, with the big spark kit that we sold for a number of years, you can also have sequential spark. So if that doesn't make sense, once again, I'm trying to cover this real high level. If you have any real specific questions, feel free to email us at support@flyinmiata.com, and one of our techs can get back to you and try to help you with greater detail levels of understanding. So back to the timing. So the computer reads the output from the crank sensor, or in the case of an NA car, the cam angle sensor has both of these built into one thing, and that's how it can still do the same job. It also reads the cam sensor so that it knows the cycle, but it uses this one to determine, okay, when am I going to throw that spark in? So there's a wheel back here. So we've got one off. This is a stock timing wheel from an NB. And you can see this wheel has little nubs on it. The sensor, as the nubs go by the sensor, there's a little magnet in there. It picks it up and it tells the computer where you are in angle of rotation. And then the computer applies to that table, and that's how it tells when to deliver the spark. So hopefully that makes sense. So let's get to the first question before we get into any more detail, because this first question is something that a lot of you guys ask, basically the same question. Ask it in a lot of different ways, but it has to do with doing timing advanced bumps on an otherwise stock, naturally aspirated stock computer car, because that's a real popular thing. And for NAs, it's free. For NBs, it's cheap. And so what that is on a stock setup with a stock computer, when you set your timing, and this is something we've talked about doing a separate video just to instruct on how to set the timing in the Miata. So we won't really get into the how-to today, just trying to keep the theory today. But when you set the timing on these, you're setting the base timing, which we can describe in a separate video, which after we shoot, I'm sure we'll link, to 10 degrees, right? What a lot of guys have learned over the years is that you can actually bump that up on a stock NA car, NB1 car, no problem, and bump that up as much as about 14 degrees and get a little bit of bump in power. And how did we figure that out? Well, this is something we've done on lots of cars over the years. We put them on the dyno, which we have a dyno back here. And you basically just start advancing the timing, doing dyno runs, and see what happens to the power. Now, one of the reasons Mazda put it on 10 degrees is because they don't know what gas you're going to put in the car. And they have to be conservative, they have to have warranties. And so if you're putting 87 octane in the car, you should probably just keep it on the 10 degrees because that's stock and that's safe. One thing to remember is factory engineers spend a lot of years in school and get paid a lot of money to get this stuff right. So, there are things in the aftermarket we can definitely do to improve on that within certain constraints, but it's always important to pay attention to the guys who got an A on the test, right? So, in our world, a lot of us performance-oriented guys, we're willing to spring for putting premium gas in there, even if we don't have a turbo. So, if you're willing to put premium gas in there, and your car's otherwise stock, you can get a little bit of a power increase, maybe 4 or 5 horsepower, a few foot-pounds of torque, by adjusting the base timing from 10 degrees up to 14 degrees. Now, I'll step back if you want to zoom in on that. One thing to note there, on that you're going to see a bunch of little hashtags, a 10 and a T. The T stands for top dead center, the 10 stands for 10 degrees, and each hash mark is 2 degrees. So that's important to remember. So when the thing is stock and you're setting your timing, you're going to set the notch on the pulley, which I'll explain in a little more detail in a second, to 10 degrees. If you want to bump it on an NA car, where you can simply twist your cam angle sensor to bump it during the timing setup process, you can bump as much as 14. Now here's the caveat. I've been doing this a long time. As long as you're willing to run at least 91 octane, and the weather's cool, 14 degrees is generally no problem. I have seen situations where at 14 degrees on 91 octane and really hot summer temperatures where you can actually still get a little bit of ping. So what I personally used to do is in the summertime, I would actually set it to 12. And then, outside of the heat of the summer, I would set that up to 14. So just, food for thought. If you're somewhere that has 93 octane gas, 14 shouldn't be a problem year round. So, what that does, another thing to stress is all these engines, they're the same, but they're all a little different. Some are more tired, some are more healthy, some have different mods, some have heads, some have cams, some have intake, some have exhaust. So, going from 10 to 12 to 14 degrees, sometimes you'll see a little tiny bump, 4 or 5 horse, all across the power range. Sometimes you'll see just a little bit in the mid-range, not that much on the top end. So it should be a benefit. What it means to you, anytime you're doing mods to your car, you're never going to know unless you actually do an A/B of your car on the same dyno with the same operator. If you really want to know, that's what you have to do. Otherwise, you're just saying, hey, this is what most guys do and this works, so I'm going to do it too, and that's great. And that's totally fine. You just have to recognize what you're getting into. So on a 1.8 NA, yes, if you're willing to run premium, you can get a little bit more. Free. On a 1.8 NB, it's cheap. So an NB, like this engine, this thing is fixed. So there is no way that Mazda gave you to adjust the timing. However, at our website, FlyinMiata.com, we have an adjustable timing wheel that we invented this a long time ago. And what we have always used it for is for a static timing retard on the turbo kits, like our stage 1 turbo kit that's 50 state legal, because you have to do that for other reasons, which we'll talk about later. A few years ago, we redesigned it and said, hey, why don't we also give this thing some range to do advance for the naturally aspirated guys who want to do that same little bit of timing bump on their NBs. And so when we did this redesign, now the thing has the span to do, the 6 or so degrees of retard for a stage 1 turbo kit, and also do, 4 or so degrees of advance for a naturally aspirated guy. And another question on here real quick, why 14? Well, one thing that you'll find on the dyno is that past 14, you just get diminishing returns. When you're advancing timing up to MBT, which is, maximum brake torque, you pay attention to how much power you get per degree of advance. And when you start to see that another degree of advance didn't really get you much more power, you're getting close to MBT or knock. And you say, okay, you don't want to take it farther. So going past 14, generally speaking, isn't a benefit. So that's why we usually just do 12 or 14 based on the amount of octane. So back to it. So I don't have one to show you here, but if you go to flyinmiata.com, you'll see our adjustable timing wheel, which is basically this, but with slots in it, so that when you have it on, you can rotate it, so that in a static fashion, you can rotate this to advance or retard the position of these nubs, which effectively advances or retards your base timing on the vehicle. So on an NB1 99-2000 engine, yeah, it's going to be the same thing as an NA. It's half point higher compression, not that big of a deal. On an NB2 with the VVT engine, I'd be a little more careful with that one because that is a higher compression engine, and so advancing the timing on a higher compression engine, and also it's VVT, so the relationship of what this is telling the computer versus what this is telling the computer is also going to affect your variable valve timing. And so you could have, basically, I've never actually done that on a VVT engine, so I don't really have a lot of advice for that. But 90 through 2000, cheap or free horsepower to do that. Couple horse, hey, it's nice, right? When you've got a 115 horse car, 4 horse is a big deal. So let's see, got that one. Let me just check some of these questions here. I guess the last thing on here is, the question, will that wear things out prematurely? No, unless you're knocking. If you've got too much heat and not enough octane, or if you have a tremendous amount of carbon buildup in here, it's causing actually pre-ignition that's, causing that, yeah, then you're going to hurt your engine. But as far as this little 14-degree timing bump, as long as you're not getting any kind of detonation or pre-ignition, it's not going to affect the longevity of the car. Remember, these are tough engines. These were originally built to basically be, a turbo engine for homologation, and then they took off the turbo and put it in the Miata, and that's one of the reasons why our turbo kit has been so awesome for so long, because we're just throwing a turbo back on a turbo engine. So they're really tough engines. Okay, so that's enough about the 14-degree timing bump. Got a lot of other questions here. Let's start going down the list. Let's see, my NA has a standalone ECU. My NA is naturally aspirated, but has a standalone ECU. What real-world benefits, if any, can my engine develop with our 36-2 timing wheel? So, as you may notice, a stock timing wheel has 4 teeth on it, on an NB. NA cam angle sensor, there's a couple teeth on it for, anyway. We have a custom wheel that we did in conjunction with our the Hydra ECUs we used to sell, which I believe will also work with some of the other standalones on the market. Check with your people for your standalones. That it's has 36 teeth with 2 of them missing, 36-2. That has much higher resolution. In my opinion, from driving them back to back, it makes the engine run smoother, and on the dyno, we are able to get more timing advance under load. And here's why. In steady state, I think it's smoother, but it's kind of hard to quantify that. When you're under load, the computer has to read these knobs and be predictive of where things are in order to fire the spark. Now, under steady state, being predictive is no problem. On a naturally aspirated car with a very linear power curve, being predictive is also kind of no problem. On a supercharged car that has a very linear curve, it's also kind of no problem. On a turbo car where the power delivery is very non-linear, having to be predictive is going to be a little bit more of a limitation, and you always have to set your timing to be conservative, right? So that you're a couple degrees pulled back from anywhere that you could have knock for safety. So by having more resolution, your prediction can be better, and that allows the computer to be, well, it allows the calibrator to be a little more aggressive, because you can get that extra timing in there with the more correct predictiveness and just get more power out of it, in short. So I don't know if that was confusing, but yes, the 36-2 wheel is a benefit if your particular system allows you to pull it off. Okay, now another thing I wanted to talk about real quick before we get into some more questions about just general timing theory. You know, what is a timing table? I wanted to have an example for you. Unfortunately, I forgot my laptop today, so I don't. But a timing table, it's a 3D thing, and it's a map that shows at any point on this three-dimensional map, for any given RPM and any amount of load, what is my degrees of before top dead center that the computer fires a spark, right? And top dead center is defined as when the number one piston is at the very top of its stroke, okay? So let's go over here to this chart. And this is very broad brush, high level. So I just want to try to give kind of an overview to a lot of guys that might not have been exposed to this concept before. Okay, so say you have, you know, your crankshaft is rotating through, you know, it's round, right? So you've got 360 degrees of rotation, right? Yeah, I know, cam and crank degrees, yeah, I know, right. But anyway, let's just keep it simple. So, and you've got your spark and you've got your computer, and your computer says, okay, when I'm going through my rotation for this load and this RPM, I go to my table, I say, okay, this is how many degrees of advance I need, boom, fires the spark. Now, if you've ever lit something on fire, you know that the flame, or if you've ever seen like high-speed footage of a flame front, you know, if you watch the high-speed guys on YouTube, right? A flame front, the spark is going to fire, and there's a kernel, and that kernel propagates out. It gets bigger and bigger, and as it does that, it develops pressure. And then at a certain point, everything that it can combust has been combusted, and the pressure will go back down, right? So you've got your spark, and there's a time delay. Now, things happen very fast in an engine, so you have to kind of slow it down in your mind to see how this is working. You've got a spark, and you got your kernel, and then it starts to build pressure, and you've got a pressure curve, and it builds and builds and builds and builds and builds, and then you've got your peak cylinder pressure. And then after your peak cylinder pressure, it falls and falls and falls and falls down to nothing, and then the next event, it does it all over again. So very roughly speaking, you know, okay, because I'm sure there's some guys in the crowd that are smart about this. What you want your spark table to do is fire the spark such that your peak cylinder pressure is achieved at roughly 15 degrees after top dead center. Roughly, okay? And this is one thing when you see guys on the dyno, they're advancing and retarding timing on the dyno. What they're doing is they're trying to find the point, how much timing can we put in to advance it, or really, technically, where can we set the timing so that as chemistry is happening and things are in motion, my peak cylinder pressures are at about 15 degrees after top dead center. Why 15 degrees? Well, and that's just something that guys who have been doing this a long time on lots of different engines have all kind of figured out. So let's use this piston for an example here. So, you know, piston, boing, 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 boing. As the piston's coming up and down, you've got your spark up here, okay? So what do you think happens if your piston's on its way up and the spark fires and you get your peak cylinder pressure while the piston's still going up? What do you think's gonna happen? Really expensive things. You know, that's when you get knock, okay? Because all of a sudden you've got pressure trying to push the piston down while the crankshaft is trying to push the piston up. As you can imagine, that makes expensive things break, okay? Now, conversely, your piston goes up past top dead center and your crank starts pulling it down. So what happens if your piston is on the way down, your spark fires, and then you get your peak cylinder pressure while the thing's already running away. So picture this. Picture you're playing tackle football, right? And your buddy's got the ball, and you're running after him, and he's standing still, and you plow him, okay? There's going to be a big transfer of energy, right? Now picture you're chasing him, he's running, and you're running, but you're a little bit faster, and so you catch him. Well, you're going to catch him, but there's not as big a transfer of energy, right? So if that happens while the piston's already on its way down, it's kind of like chasing its tail. it's not going to produce max torque on the crown of the piston, which in turn pushes the rod, which turns the crankshaft, which turns the engine. So you're not going to, it's not going to hurt anything, but it's just not going to make much power. So what they've figured out is, because this is a rotation, you know, you don't want that peak to be right at the top, because right at the top, if you've ever turned one of these over and watched the piston, it kind of lags a little bit at the top before it goes by. It's like, and there's a little bit of lag right here at the top. So they've just figured out that somewhere around 15 degrees after top dead center, when this thing is just starting to go back down, that's when, if maximum cylinder pressure is applied right at that point, you're going to have the most possible power on the piston to turn the crankshaft and deliver power through the rest of your driveline. So clear as mud. So your timing table's job is to be calibrated such that your spark fires at the correct time that produces maximum cylinder pressure at the correct time, so that you have this. Now, obviously at full throttle, that's obvious, but even off throttle, when you're just cruising, you know, that's going to affect your response, because even if you're just cruising steady state and you just give it a little bit and you just want to, you know, maybe pass somebody real casually or speed up just a little bit, still having this correct is going to affect that little bit of transient response right there. So, you know, that's still important too. Now, off throttle, there's also a lot of considerations for emissions, and I'm not going to get into that at all today, but you know, rest assured that emissions definitely have a lot to do with how the factory engineers calibrate these tables. For our purposes, we're just talking about the power end of it today. So that's kind of a basic overview of why a spark table is important, what you're trying to accomplish with a spark table. So let's get into some more questions. Bear with me for a second. Okay. Let's see. With a standalone ECU like a Megasquirt, do you have to manually input the actual timing that you see with the timing light into the software? Not exactly. Setting the mechanical timing correctly is not enough with a standalone. Why is it enough with a stock ECU just to make sure your mechanical timing is correct? Okay, fair question. Here's why. With a stock ECU, the user has no control over anything, right? Miata ECUs, NAs, NBs, have never been able to be hacked into successfully. NCs and ND1s, you know, we've been able to recalibrate for our forced induction kits, but NAs and NBs, you're not getting into that computer successfully and reliably. So since you have no control over that ignition table that the factory engineers developed, the only control you have is your static timing setup, right? Either back here on NA and B or with our adjustable timing wheel, or NA6, NA8 adjustable timing wheel on the NB. So whereas with a standalone, it's a different story. With a standalone, you have full control over everything. And trust me, it's a lot easier to make it worse than to make it better. And that's why, you know, where you spend your money on calibrating is huge, huge. Anyway, soapbox that I won't get onto at the moment. But with a standalone ECU, what's very important is that if I say standalone ECU for this RPM and this load, I want you to fire at 10 degrees, okay? You want it to fire at 10 degrees, right? And the only way that you're going to know that is if you calibrate. So when you're installing a standalone ECU, you have to do certain calibrations, base timing, throttle, you know, depending on your ECU, there's a number of them. And when you calibrate it through the manufacturer's instructions, that says, okay, if my computer says 10 degrees, it's 10 degrees. So now I can go over and build my table and say 10 degrees, and I know it's 10 degrees because you've calibrated the two to agree with each other. So hopefully that makes sense. Support at flyinmiata.com if you need any more help with that. Do we have a question, Kyle?
One question from Facebook. Customer with a 90 NA6 trying to check their timing, but couldn't find the timing mark. Any suggestions on?
Yes, and that's actually on here too. So the thing was, I'll go ahead and jump to that one now. The guy or girl can't find the timing mark. So here is a stock, I believe this is an NB damper. Here, I'll describe some things so the camera can come in close. Trying to social distance from the cameraman today, so I don't have to talk through a mask for 45 minutes. So, Travis, if you can zoom in there, you'll see on all the 1.8 dampers, there are 2 notches, okay? On the 1.6 dampers, there is 1 notch. So the 1.6 damper is easy, 1 notch. 1.8 dampers, 2 notches, there's only 1 of them you'll pay attention to. And just to be clear, the one you pay attention to is the one that's on driver's right, okay? That's the one you pay attention to for hanging a timing belt. That's the one you pay attention to for setting your base timing, the one on driver's right. So I would, anyway. And on a lot of these, they're old and they're corroded and they're full of gunk and you can't find it. But the notch is actually cut into the metal. So you may just have to go around, if it's full of gunk, you know, with a wire brush and clean it up. Find where that notch is cut into the metal. And then I would hit it with a paint pen. Because when you're shooting it with your timing light, you want to be able to see it real clearly. So it's there, you know, unless the thing is so rusted that the metal's fallen off. It's there, and you just got to get in there with a wire brush or something, find that notch and mark it. New from the factory, they're painted. You can see here the one that's on driver's right is painted, right? But oftentimes as they age, that goes away. So make sure to identify that notch because that notch is very important. Like I said, separate videos hopefully to come for setting base timing. I don't know, have we done one on hanging a timing belt yet? That'd be a good one for us to do too. So those are things that we can definitely put on the to-do list. Does that take care of that one? Yep. Okay. Okay. Let's see, cam and crank sensors. On the NB, the crank sensors are very reliable. The cam sensors are very not reliable. For any Miata, there's a couple things I like to keep in the glove box. One of them is a spare main relay because they like to cook. And not to go down that rabbit hole, but they cook because the wires under them are also cooking and it's like a chicken or egg with resistance building up and heat. So if you cook a main relay, take out the box, look at the wiring, replace if it's damaged, replace your relay, and keep a spare one in your glove box. You'll wish you did someday. The other one on NBs is a spare cam sensor. These things also do fail with heat, and there's really nothing to be done about it. We only use factory OE stuff for these sensors. Personally, I being stuck on the side of the road because of a questionable, you know, who knows where it was made sensor to me is not a fun day. So, but for NB owners also, it's wise to keep a spare cam sensor in the glove box, and we do sell both new cam sensors and new main relays. It's just what it is. You know, that's just maintenance items on these things. Like also, you know, on 99s, coil packs are maintenance items. It just is what it is. So, okay, we covered can't see the lights. Where do you shine the timing light? So, you shine the timing light on that notch as it lines up with here. And like I said, we'll do an instructional video later, but the driver's right notch lines up on the T when you're hanging your timing belt. When the engine's running and you're setting your base timing, the driver's right notch lines up on the 10 stock or, you know, the first or second notch over for 12 or 14 degrees. So as you're hitting it with your timing light, which I can describe somewhere else, the light will strobe and you'll see those things line up, and then that's how you can clock them so that you can get it exactly where you want it to be. Let's see, is timing on a 1.6 any different than on a 1.8? No. You know, these things all have the same firing order. 1, 3, 4, 2 is your firing order. You know, the fundamental architecture of B6s and BPs is the same. You know, it's just a little bit bigger. So it's fundamentally the same. Really, the only difference in timing is, you know, the NA you can adjust, the NB you can't unless you buy our adjustable wheel. Is the Miata engine really non-interference? Correlated sort of question-ish. Yes, all stock B6 and BP are non-interference. And what that means is if your timing belt were to fail, you're not going to bang valves into pistons. So worst thing, you get your tow, you hang in your timing belt, and you go on your merry way. Some other engines are interference, so if your timing belt were to fail, all of a sudden you're going to have hard contact between your rods, or sorry, not your rod, your piston and your valves. And kind of what that means is if a valve was at full extension on one of these engines, say there's no timing belt, the valve is at full extension, I can rotate the crank and the piston's gonna go up and down and it's not gonna hit the valve. On an interference engine, if a valve is at full extension and you rotate the crank, they're gonna smack into each other, and that's when expensive things happen. Here's a good one. Is anything specific to the Mazda speed? Well, it has a turbo. Obviously, the ECU calibration is different because it has a turbo. But fundamentally, I mean, they've got the same injectors, same sensors. Basically, a Mazda speed, it's kind of a conglomeration. It's got 99 pistons. You know, it's got the it's got the NBFL, the VVT, main bearing support plate. So it's kind of a homologation of earlier things that they've put back together to be appropriate for putting a turbo on it. But on those, there's really nothing you want to do with the timing until you're ready to get a standalone ECU, honestly. I wouldn't try to get hot with, you know, adjusting the base timing on those so much, because the factory calibration is a little lumpy bumpy, and I would, best thing you can do with one of those is just, you know, our bolt-on little enchilada package of all those parts is awesome, or if you want to take it all the way to a standalone, but I wouldn't really try to mess with the timing on one of those. I don't think you're going to get much out of it. Will a stock ECU recognize a trigger wheel with more teeth? No. A stock ECU is very specifically calibrated to look for a very certain thing. So if you change that certain thing, like adding teeth to the wheel, the stock computer's gonna be like, I don't know what to do. And it's gonna start either just nothing, or worst case, throwing spark at completely the wrong time, which makes expensive things happen. Okay, here's one for Kyle. If I never remove the timing belt doing a water pump job, do I need to set the timing?
I would like to see that happen.
That was kind of what I was thinking.
Timing belt. I don't think you can do a water pump without pulling the timing belt.
Yeah. So Kyle, our awesome, excellent mechanic, says that he doesn't think you can do a timing belt job without, or a water pump job without pulling the timing belt. So if you do, we would love to see it.
And if you pull your belt, you don't have to reset any ignition timing. You just have to get your mechanical timing correct.
Right. Regarding the mechanical timing. Because remember, mechanical timing and ignition timing are two different things. Mechanical timing is the relationship between how your timing belt is hung, how your cams are timed, and top dead center. Okay, so that's your mechanical timing, which is defined by hanging the timing belt correctly and then on an NA setting the base timing correctly. Your ignition timing is defined by the mapping in the computer, okay? So remember, mechanical timing is different from ignition timing. Okay, so here's a turbo question. How much timing should I run, advanced or retarded, for my 94 turbo? So now, advanced and retarded, let's cover this real quick. Let's just say this is not to scale. I am not an artiste. So, but let's just say, for the sake of argument, that this is, let's say that this notch is 0 degrees top dead center. So when your spark fire, or where you are in your rotation, okay, if you're rotating this way, all right, clockwise, and you're kind of, here, let's do this. Going in that direction. If you're rotating that way, this is top dead center. So if you fire advance, well, there's before top dead center, which is over here, and then after top dead center, which is over here. And timing is always going to fire before top dead center because there's that latency of the flame front. Anyway, advancing your timing is advancing it ahead of, so if I'm, let's say, you know, not to scale. So let's say I'm 5 degrees advanced, and, you know, back here, I'm 10 degrees advanced, et cetera, et cetera. How many degrees before top dead center is it firing? Now, as far as advanced versus retarded, where you're going to see that is like if you're adjusting your cam angle sensor, pragmatically, if you're advancing the timing, you're moving it this way and making the numbers bigger. If you're retarding your timing, you're moving it closer to TDC and making the numbers smaller, right? So hopefully that was clear-ish. But back to the turbo thing. With a turbo, you need to, because of the cylinder pressures, as your cylinder pressures increase with load, your flame front is going to behave differently, right? Things are going to happen faster. So with a say for example, you're cruising down the road. I might fire the spark at 40 or 50 degrees if I'm just lightly cruising down the road, because that's how long it takes from the time the spark fires to lining up that peak combustion. As I increase my load, things are going to happen faster. And so you need to move your spark closer to TDC, and there's a couple things to. So in a perfect world, you would always set up for maximum brake torque. With naturally aspirated cars, a lot of times the supercharged cars-ish, you can do that. With turbo cars or some supercharged cars, you can't do that because you're knock limited. And so even though this is the ideal place to be, sometimes you run into situations where if I move my spark event too far that way, it actually is, it knocks. And so instead of being perfect world, I want to set my spark for where it's going to hit MBT, says I'm limited by spark, so I need to move my spark event closer so that I'm not going to have a knock because things are combusting while before the piston is ready to start going that way. To keep it simple. So just for example, like I said, cruising down the road, you could be 40, 50 degrees. Light load, 30-ish degrees. On a stock Miata at full throttle, it's depending on the year of the car, probably going to be somewhere between like 22 and 28 degrees. Full throttle for a naturally aspirated car. On a turbo car, say you're running 10 or 12 pounds of boost and you're running 91 octane gas, you might want to limit that to maybe 12 degrees, right? On 93 octane, you might be able to get 15 degrees because you've got a little bit more octane to keep it from, octane is resistance to burn. So as your octane goes up, the fuel is less resistant to burning, so you can be more aggressive with it. If it burns more readily, you've got to be more conservative to stay away from knock, all right, high level. So on a turbo car, it really, it depends on how much boost you're running. It depends on your fuel type, etc. But we have really well-developed maps for all this from the Hydra days that they're pretty well established. That if you're really interested in that kind of thing, support at FlyinMiata.com and we can help you out there. But remember also that especially in a turbo application, timing is not just linear. Let's see how I can say this and keep it simple. Here's a real simple way to look at this. And so you're familiar with horsepower and torque curves, right? Really what a dyno is measuring is torque, and then there's a formula to convert it into horsepower, and they always cross at 52. So say you have a torque curve, and say your torque curve kind of looks like that. Say you might also have a torque curve that's kind of like that, So some torque curves are going to peak in the middle, some are going to, anyway. But the thing to remember is that when you're, and this is kind of a rule of thumb for if you're doing any dyno tuning, your timing curve for whatever this dimension is, because let's pretend this is two-dimensional for a second, which is not on a map, but let's pretend it is. Your timing curve under load, really just think about this full throttle under load, is pretty much always going to be the inverse of your torque curve, okay? So where your maximum cylinder pressures are, that's your maximum torque. Because that's where your maximum cylinder pressure is, that's where your least amount of timing advance should be, right? So high level, roughly speaking, they're always going to be inverse. So for example, say this is your torque curve, then your timing curve is going to kind of be something like that. And this is kind of odd shape. I'm just trying to pencil something out to show the difference. So as far as the turbo cars, when I say 12 degrees, that's going to be right there. It's not going to be 12 degrees across the board, because as your torque falls off, you're going to be able to put more timing advance back into it in order to maintain power on the top end, right? So, and this is something that for all you guys that are hiring people to tune your cars, something to keep in mind when you're watching them work. There's a lot of really good guys out there that know what they're doing. There's a lot of guys that are kind of winging it. But one thing to remember is when you're developing a timing table or a fuel table, or really any table in a standalone, the end result should be pretty smooth, okay? You're gonna have hills and valleys. You should not see the Swiss Alps, right? If you see the Grand Canyon and the Swiss Alps, something is wrong, okay? The way an engine develops power, there will be hills and valleys as the volumetric efficiency changes, as the cylinder pressures change. But if you're seeing Grand Canyon and Swiss Alps, so anyway, enough about that. More questions. Getting down here. Does the Woodruff key need to be replaced when doing a timing belt change? Not unless it's damaged. If you look here, here's a Woodruff keyway. So, and there's the Woodruff key, which goes in there, which is a little square thing that kind of mates up to that. And then it also, keys into the other parts that are being bolted onto it. Steel parts like that, they don't need to be changed unless they're damaged. Now on early 1.6s, on the short nose cranks, and even some 1.8s where guys didn't properly torque this bolt when they did a timing belt job, you'll see damage there because wobble started to happen. And when it starts to wobble, it's kind of like a tooth. Once you got a cavity, it doesn't get better on its own. It just gets worse. Same thing with Woodruff keys. Once they get some damage, it's only going to get worse. And so if you see that a Woodruff key is damaged, yeah, replace it, because you want that to be tight. Your timing depends on it. You don't want your timing to be bouncing around. If your Woodruff keyway is damaged, there are some things guys can do with Loctite to try to fix it. Sometimes it works, sometimes it doesn't. Sometimes you got to replace your crank, which is not fun. But, it sure beats putting it all back together and having something be wrong, because it's, do it nice or do it twice. So, okay. So we're not going to show you how to set timing today. We'll do that in a different video, just looking at questions. But one other thing I will check on here, talk about static timing retard with the turbo. We talked about how we have the static timing retard potential to advance it for a naturally aspirated setup. With our stage 1 turbo systems, the inverse of that is also you can do a static retard. So, you're moving the notch back closer to 0. Yeah. And the reason you do that is because you have no control over the factory timing calibration, you have to set things so that they're safe at all points. So if I'm putting on a stage 1 turbo system and I'm running premium fuel and I'm going full throttle, whatever the factory computer said is defining as that's my timing advance at torque peak under that amount of load, 6, 7, 8 pounds of boost, we need to move this so that that output is safe. And then everything else in the map it just is what it is, because we have no control over everything else. So we're kind of setting it to the lowest common denominator for safety and then accepting everything else is what it is. What that's going to mean is that off boost, yes, you're going to lose a little bit of response. That's the trade-off. And that's because in order to make this a 50-state legal kit, there cannot be any user calibratable stuff. That's how we have to do it. So, kind of is what it is. It's a trade-off. As in modifying, there's pretty much always some sort of a trade-off. The question just, what is it, and is it something I can live with? And so in this case, We are hoping to, we would like to come up with a solution for that. It's something that's on our radar. If we do come up with a solution that kind of solves that, we will absolutely make a ton of noise about it, because that would be a really big deal. So it is something that's on our radar. How does timing affect fuel economy? It's kind of like a bug hitting the windshield, slowing you down. But what I will say is where it could make an effect is because if your timing is way low and you're losing that response, you're going to be spending a lot more time doing this, trying to go somewhere, which is going to pump a lot more throttle pump fuel into the engine, which is probably going to reduce your fuel economy. So in a roundabout way, I think having your timing really low would probably reduce your fuel economy, just because you're having to put a lot more effort into loading up the engine to get it to do what you want to do. But not that big of a deal. What happens if my timing is wrong? Well, if it's too far retarded, you lose power. If it's too far advanced, you break things. So simple, right? So you want to have it in the right spot. Fortunately, these are tough, and they can take a little bit of abuse. It's not like a rotary, where if you screw up your timing on a rotary, you're going to be seeing your apex seals pretty quick. On a B6 or a BP, it can take a little bit of abuse. You don't want to abuse it, but when you're calibrating it, also, you don't have to be fearful of it like you do when you're calibrating a rotary. So let's see. And then the last one, change the timing belt on my 95. Everything seemed to be timed and aligned until I reassembled everything, and the car would start for a second and then stall out if I didn't rev it. Could it be something other than the cams not being timed? Absolutely, it probably is, because if the mechanical timing with the cams is off, it'd have to be off a lot for it to not run. I mean, you can go a tooth or two in either direction, and we actually sell an adjustable timing gear to do exactly that, so you can optimize your cam timing of how the air flows through your engine. So having it off a tooth or two, it's not going to make the car not run. It might not make it run well, but it's still going to run. So I don't want to go down that rabbit hole, but a lot of times what we just see guys do is on the two fuel hoses, they just get them on backwards and they don't have the fuel going down the right pipe. Or, or maybe the mass airflow isn't hooked up. Guys will try to start it before they hook the mass airflow sensor back up. Well, that's not going to work. So there's a lot of reasons why that could be, but hanging the timing belt is probably low on the totem pole. Definitely check, but it's probably low on the totem pole. So I think we've covered pretty much everything we have. So let's check over here with Kyle and see if we have any more questions that have come through.
All the questions about timing have been addressed.
Okay. So speaking of timing, how are we doing? We're at 2:52. So if there's no more questions, I think we should probably go ahead and wrap it up. Yeah, so we're good, Kyle?
Yep.
Okay. Well, thank you everyone so much for being here. Thank you for submitting this nice thick list of awesome questions. I hope the things that we were able to talk about today, just to kind of help you give you some big picture views. Once again, for real specific stuff, support at flyinmiata.com. We can help you to the best of our ability. And check out our website. And we will see you guys next time. All right. Take care.